Okay,
There.
let's try. Okay.
Yeah.
Okay.
Good to go.
Okay, works great. Hey, good morning. How are you doing? Nice, nice. I went to the Smith. Yeah, Smith was the name of the pub or restaurant. No, it was nice. Like a very tasty burger. So it was nice.
Did you say that yesterday's lectures are on your GitHub?
Yeah, if you go to the, I mean, you can, yeah, use,
Really, for
yeah, you should scan and because I included in the same repository both the presentations and the code, so you can be access.
so everything's there.
Yeah, and the slides as you hear.
The photograph and yesterday.
Yeah,
This.
this is the code. I mean, the instruction to build the knowledge graphs yesterday, and yeah, the slides are at the beginning of the section. So here.
It's really well put together. Thank you.
Thank you so much.
I have like oh yeah. I like it. So amazing.
I can say I have a portable that. I have this one.
Just basically helpful. He's like her mom's like thank you.
Yeah. What do you listen to? You never listen to music, you just use your. I'm not gonna start yet.
Mhm.
That's what I came back. So, cause like I haven't watched them. So those are wet. So.
Come on.
How are you?
Hi. Yesterday I sent to your. What's the difference between a contract and a license?
Well, basically the license is some of, you are in some way enabled by the city to perform some activities, so to sell something, right, for instance. And the contract, it's a specific, I mean, it's a specific way to, for instance, sell products to the public administration itself, in the sense that when you have the license, you can sell your pens to anyone, right, in the city. But when you establish the contract with the city of Chicago, then you establish how much pens the city of Chicago buys from you, right? And so it's a specific relationship, specific market and commercial.
You have to have a license to get into a contract. Is that it?
Yeah, I mean, I think that
That's the point of the.
yeah, that was the point.
State to the.
Yeah, exactly. I mean, you should be enabled, right, to perform your activities and provide services and products. So, I mean, this is my assumption. So in theory, you should have a license to make some, establish some contracts with the city of Chicago. This was interesting because there are very small cases, right? Very little cases in which these anomalies happen, right? So probably the normal situation is that, okay, you have a license that will end in the future. Before the ending, you will provide your services and also establish some contracts with the city of Chicago.
At some point this week for the data sent out.
Doesn't coordinate very well with that which signs contracts.
I mean, I would say maybe it's an issue that is just related to the data that have been released. Maybe they have been updated in the next release because they release these CSV files. I don't know if every week or every month, right? So sometimes there could be some issues because the data could not be complete. It can happen. In the sense that I'm not saying that there are some illicit activities, right? But maybe it's something related, specifically related to the data. So that's what the data at that moment says, right? So
And the two departments don't share like an identifier for
That's so funny, yesterday, like.
no, you don't have shared IDs for both contracts and licenses and also for the organizations, right? In the sense that the organizations that are mentioned in the license do not have the same ID of the organizations that are mentioned in the contracts. So this is one of the main issues to understand this type of anomalies.
Are the contractual details in any way connected to license?
Yeah, I mean,
License to sell pens, track for pens?
yeah, I mean, you could analyze at that level, so at the topic, right, of the contract and the license, because you have the details, you have the descriptions, so you can make much more assumptions in the sense that this could be something that could be very interesting for extending the work that I did until now. Yeah, definitely.
Yeah. There's enough information that says that maybe the posting times yesterday at like 5:12, but the license type is connected to the contract in
No.
any way either.
No, there are some metadata, including, for instance, the license type, but
No,
it is
she's
not a
not.
keyword that is used to identify the
So
contract.
exposed.
Yeah. Yeah, probably. I mean, the main, I don't know if they are managed with different systems, right, within the city of Chicago, but in any way, you do not have a clear connection, right? And once you don't have a clear connection, it becomes hard, right, to detect anomalies and issues. This is why the graph comes to play, and you can play an interesting role, right, to detect these situations. Yeah, but the good thing is that you can experiment a lot, right, with this data because they are open, they have a good amount, right? So, sorry.
I'm volunteering here to help with the speech.
Okay, good.
Basically, there's going to be like a virtual Q&A as well. So there's going to be like questions that come in.
Mhm.
So basically, however you want to run it. If you like, do you have a Q&A session at the end or anything?
No, I mean, if you have some question during the presentation, feel free to interrupt me.
Okay,
and,
great.
ask.
I could just, yeah, I'll raise my hand then and
Yeah. Sometimes I will put my face to
Okay.
see if there is some questions or some curiosity or something else.
Okay.
So
great. And then, yeah, there's the socks there. Did the guy tell you?
yeah, he told me that I have to.
Okay, great. Yeah, and if there's anything else you need help with, I'm here to help. So.
Okay, great. Thank you very much.
Question.
Yeah.
You have the structure like federal data. You would add all the issues.
I added some properties. For instance, when there was a connection between in the license data source, when there was a connection between a person and an organization, you usually add the role, right, of this person within the organization. So this is an example in which I attached a property to the relationship, right? Because I mean, the role is not something that is related to the node itself, but it's something that has a meaning when you identify the connection with the company. So this is an example of a property that I use for relationships. And obviously I use the properties for incorporate the scoring, the similarity score between the person nodes, for instance. So I put this information I attach this information to the edge. So this enables also to perform to running the community detection algorithms, because you have to specify which relationships they have to use to build a community. And in the case of Luane, you have to specify which property contains the strength of the relationship. So in this case, it's another case in which I attached the property to the edges. Yeah.
Start with
Yeah. Yeah, but yeah.
Yeah.
Okay, great. Thank you. Oh. Thank you. Yeah, definitely.
Alright. Yes. Yeah. But would have been too wide to cast. And put us out for that. So. We gotta work on it. So, yeah. I'd get it to give to our. I'm relatively. Yeah, I can look at the pieces. But I have. So it's just like, oh yeah, I know what the gas is. And how are you?
Yeah. Yeah, I mean, in terms of streaming, there is an interesting feature. For instance, when you continuously integrate data into the graph, interesting feature called the change data capture on Neo4j, which basically provides information about the last nodes and edges that have been integrated in the graph. Yeah, I don't have experience. It should be interesting to investigate, but I do not have experience on this.
Yeah, I'm interested.
I mean, I have something similar using this feature as I mentioned you before, but I mean, we can discuss later after the masterclass if you want. Okay, it's 9:01 in the morning, so thank you very much to be here for this masterclass dedicated to graph neural networks. My name is Giuseppe. I work for an Italian consortium that actually provides infrastructure for many public administrations in the north of Italy. And before starting, if you would like to connect with me on LinkedIn now or after this presentation, feel free to use this QR code. And if you would like to just leave a note in saying, okay, I participated in your graph neural network session, it would be nice in order to recognize you. And these are the main stages of our journey today, right? In order to understand how graph neural networks work, we will focus at the beginning on a bit of theoretical part, right, in which we'll try to build intuitions about graph neural networks. Then we will focus on the layers in the sense that probably in your experience, you heard about a lot of different architectures, including graph convolutional networks, graph sage, graph attention networks, and so on. And we will try to build intuition about their differences. And finally, we will see some applications related to the graph neural networks. Some of these applications are quite common, including node classification and link prediction. Other ones are, let me say, on the edge, because there are some interesting researches in try to combine graph neural networks and large language models, and we will have a look at it. And with this QR code, you can access to the GitHub repository in which these notebooks related to these 3 different sections are provided. Everything is on Colab, so basically you can access quite easily. And you also find the slides of this presentation, so you can follow these slides directly on your laptop. Unfortunately, in this presentation, we will have a look a bit of some matrices and some math, but I mean, it's inevitable when we talk about graph neural networks because they still work at a very low level. So in order to understand how they work, I should provide some details about matrices and math, but I will try to guide you and I will not leave you alone during this, when I will show all this stuff. In order to contextualize graph neural networks in the field of machine learning and deep learning, we have to consider that in the context of graphs, like in traditional machine learning, this is the traditional process, right, in terms of learning. So basically, we have an input set of data, in our case, our input graph. We usually, using a manual feature engineering process, we extract the main features, right, related to this graph in terms of a different level, in terms of nodes, edges, and the graph itself. Then these manually engineered features are feed basically our learning algorithm, which is basically apply its own process in order to perform the prediction. Here you can have you can have a look at a Colab notebook. I mean, I will not go through the details, but in order to understand what does it mean extracting features from graphs, you have this Colab notebook in which, starting from the well-known Karate Club graph, you will have a look at how different features are extracted, right? We have information about centrality measures, right? So you can see the differences between the different nodes according to these centrality measures. Some of these measures are quite understandable in the sense that the size of the node is related, for instance, to its degree, right? So to the number of connections. Sometimes there are more advanced algorithms like the eigenvector centrality, which is the base of the well-known PageRank algorithm, in which the centrality measure is not related only to the numbers of the connections to the node, right? But also to the importance of the nodes I'm connected with, right? So this dimension is considered in algorithms like eigenvector centrality. So you can have a look and you can explore this notebook. if you are interested in it. So let me.
How can we find that link?
Yeah, I mean, you can use this, and you can go to the theory section of the README, and you find something like how to extract manual features from the graph. Yeah, I use the network X because it's quite easy to use for this kind of purpose. Yeah, yeah, it's basic, but it's very useful to get intuitions about the different results obtained with these algorithms. So let me go back, and we talk about traditional approaches for doing machine learning also on graphs. But as you know, I mean, the trend and the breakthroughs about machine learning was represented by the deep learning, and particularly the representation learning stuff. So in the previous process, basically, we manually define the features that we want to extract and that we pass to the learning algorithm. But in the context of representation learning and the graph representation learning, the exercise is different, right? We want that our learning algorithm learns also the features in order to identify the most suitable information to perform the downstream task, right? So the key idea is that the representation of the nodes and the edges and the graph itself will be learned during the training process. And these learned features will be used, right, for the downstream tasks that could be node classification, link prediction, and so on. So this is the context in which, this is the area, the umbrella under which graph neural networks are positioned and are located. So let's go deeper on the theory. And actually, I would like to ask you some volunteers that will help in my explanation to provide details about message passing neural networks. And I prefer someone who is in the front row. So the 4 guys in front of me, I would ask your names. Shu. Okay, but I will speak. No, I need just your name. Penny. I mean, it's too hard. Okay, let me. Okay, Jeff. And yours, sir? Mark. Okay. I mean, I will speak. I promise. But just to, build intuition, it's useful for me to have your names. So let's move on. In order to understand the key elements of the message passing layer, which is one of the building blocks of traditional graph neural networks, we will try to use 3 different ingredients. The first ingredient is represented by these 3 blocks, which represent the main steps of the message passing learning algorithm. And as I promised, I have an equation, right, that describe the message passing propagation within the network. And then we will use this graph, right, in order to understand how the message passing works within a real graph. So the final goal of the message passing layer is to basically learn the representation of all the nodes within the graph. And for the sake of simplicity, we will use just the central blue node. And this representation should in some way incorporate the representation of the neighbors. So basically of the representation of the nodes that are in some way connected to the blue one. So if I am the blue one, you guys are my neighbors. Obviously, in order to get the final representation, I have to start with my representation, my initial representation. And let's imagine that the information that I have, for instance, are related to the knowledge that I have about, I don't know, graph databases, right? So this is the set of features that I have that characterize myself. And regarding your features, guys, we talk about the same thing, right? We talk about your knowledge, for instance, about graph databases. So here, you see the progress in the equation when I describe each of these ingredients. So the first step is try to ensemble a sort of message, right, that describes how we pass the information to each other. So the key idea is that we want to create a message according to which I pass my knowledge related to graph databases to you, and you pass your knowledge about graph databases to me, right? And actually, the generation of this message of this first step could be quite flexible, right? Because we can consider different dimensions. For instance, our features, so our knowledge about the knowledge graph databases and so on, but we can also consider features that are attached to the edges, right? In that sense, we can consider how do you trust, right? For instance, my knowledge about this specific topic. So we can decide how to combine all these ingredients to exchange our messages. But the key idea is that I will transfer information to you and you will transfer information to me, because this is the way in which we are connected. And the next step in the message passing layer is something called we take the message and we parameterize the message to do a multi-layer perception. Actually, this was my face when I started to read this expression, parameterize something through a multi-layer perception. Who has the same face when you heard about this? Okay, not so much. So you mean that you know very well, this concept of parameterize something, but I will try to recap a bit of linear algebra in order to align all of us, right, about this topic in order to grasp the main ideas of what happens within a graph neural networks. Let's imagine that this matrix, a 5 by 5 matrix, right, is the representation of the initial nodes in a graph, right? So ourselves. And these initial features actually do not convey a lot of information, right? Because the only difference is that you have a 1 located in a different position for each row, right? You can see here. So this matrix does not convey a lot of information because the only information says it's, okay, we know different things, but we do not have a clear idea of how these things are related or are similar or are completely different. We are just different. So in traditional neural networks, including neural networks that are used in the convolutional neural networks, in transformers architectures, one of the key processes is basically try to parameterize the features by multiplying this matrix, right? This initial node features matrix with these basically parameters. When we perform this multiplication, right, we obtain this result. And how we obtain this result? Well, just to recap some of matrix multiplication operation, the idea is that in order to obtain the value on the top left, right, I have to multiply the element here in the 0, 0 position and the other element in the 0, 0 position. I have to multiply these elements and then multiply these ones and then multiply these ones and then multiply these ones and then multiply with these ones, right? And everything was 0 apart from this one. So I put this value here. And I perform the same operation here. So basically, I multiply this row for this column, element by element. And considering that I have a 1 initialized here, the only value that is put there is 0.02, right? So this is the way in which we obtain our parameterized result after this multiplication. And this is an interesting process, right? Because as you can see here, you have a 1 initialized in the 4th position. It means that the 4th row in this matrix is positioned here in the 1st row of the result. And the same thing happens here. And apparently this stuff, it's, just a mathematical exercise. But what we obtain during this simple exercise is that the initial features that I have here are translated in a different vector space, right? In which now the information, it's much more informative in the sense that we do not have just 0 and 1s, but we have these numbers, right? And these numbers actually do not mean anything by themselves, but these numbers actually start to mean anything when we have a distributional perspective in which we compare these numbers, right? So we were able to obtain a different representation of my nodes in another vector space. But the most interesting thing is that during the training process of a neural network, these numbers will change, right? And these numbers will be updated in order to fit the downstream task that we want to address. So this number will change at the end of the process. And finally, we should be able to obtain a vector representation for the nodes that in some way is meaningful, right? And meaningful means that similar nodes in the graph, in theory, should have similar numbers in terms of vector representation. Actually, I mean, in a traditional neural network, we also include a linear activation function, which is basically an operation that allows us to obtain a result that we cannot obtain with just a matrix multiplication. So the ReLU function basically drop the negative values, right? So it takes the resulting matrix and put the negative values to 0. So this is what does parameterize something to a multi-layer perceptron. And so anytime you will find in a paper, a graph neural networks paper or other papers that uses this expression, you just have an intuition of what does it mean. I just multiplied initial features for a parameter matrix that allow us to have a learnable representation of the data, which is something that is really useful for the context of representation learning. So that's the idea. So that's the meaning of parameterize something to a multi-layer perceptron. So we condense our equation, right? We have a complex stuff here, and we just use them to describe the message. And then we describe the aggregation process. So the key idea, as I mentioned before, is that we assemble this message, and then we use this message to transfer information. In this case, from this image, you are transferring information to me, right? So you are transferring your knowledge about graph database to me. But this operation in graph neural networks is performed simultaneously for all the nodes within the graph, right? So basically, you transfer your information to me, I do the same job, and the same thing happens, right, to all the nodes within the graph. But for the sake of simplicity, let's focus on what happens here. So this is the operation that this means, and this is something that is called, I mean, the smartest guy called permutation invariant function, right? And again, the same face. Who has the same face? Raise your hands when you heard something like permutation invariance function. Okay, maybe more than before, but yeah, to get an idea of what does permutation invariant function means, actually, it's a complex way to say, let's imagine that we want to aggregate, I mean, I'm aggregating your knowledge to me, right? So how I aggregate, if I apply, for instance, a sum operation, it doesn't matter if you change the seeds, right? Because the sum operation is invariant to the permutation. And so this idea of permutation is that we are a graph, right? But if we switch our positions, we are the same graph from the relational level perspective. So if I do not use any labels to identify ourselves, if we change the position, we are the same graph. So the important thing to understand, if graph neural networks are able to recognize isomorphic graphs, so graphs that have the same relational structure. So in the case in which you switch the position of the nodes or you use different labels, the result of the graph neural networks will be the same, right? So they are great in doing this exercise. They are less great in recognizing non-isomorphic graphs, right? There are some situations in which graphs with different relational structure are recognized by a graph neural network as the same graph. And that could be a problem, right, in some way. But this is the idea. And this is idea of equivariance invariance. It's really interesting. I think one of the most interesting, basically, research line in deep learning, because this idea of equivariance of invariance is also applicable to other architectures, right? For instance, convolutional neural networks. But in this case, the transformation is different in the sense that for graphs, we talk about permutations, switching nodes. But in the case of images, we talk about translation, right? We expect that a convolutional neural networks provides the same result as output. For instance, this is a cat. Also in the cases in which this cat is translated, right, in the space. So this is particularly interesting because probably it's the only deterministic operation that we can see within deep learning architectures, in the sense that graph neural networks will always be able to learn functions that are permutation invariants. So any type of graph neural networks beyond its own parameters and so on will always be able to recognize graphs with the relational structure. And at the same time, convolutional networks will be always able to recognize the same image in the translation. So this is something that could be interesting and open, I think, a lot of interesting research, new research lines. So let's finalize this stuff. If you are interested in this idea of permutation, equivariance, and invariance, or translation, equivariance, and invariance, I publish a medium of article in which I try to use some graphical stuff in order to clarify all these points. So let's finalize our process. So the idea is that, I mean, we aggregated the messages. So basically aggregated the knowledge that comes from you guys. And then I have to decide how to update my knowledge, considering yours, right? And I mean, we can be flexible. Sometimes, most of the cases, what we do is taking my features, so my knowledge, concatenate the feature vector resulting from your knowledge, and then reparameterize this result through a multi-layer perceptron. So let's think about what we made, how we transform stuff in a learnable way. We basically make the message learnable, but we also made the updating operation learnable, right? So all this stuff will be updated during the training process. So we reach, right, the final results. We decided how to ensemble the message, how aggregated the information, and how to update, right, the result to myself. I have a question for you. What happens if stack, based on the considerations that we made, what happens when we stack a new message passing layer into the network? What happens to myself, for instance? How my representation is updated according to your opinion? I don't know if the question is clear, because obviously when we stack a new layer, right, something happens. So it means that my representation is updated. Do you have an idea?
Change forget to multiply in the null matrix.
Sort of. I mean, I have this present for you. I have a lot of ones, right? So I can. Thank you very much. So the key idea is that when you stack a new layer in the message passing neural network, what basically happens is that, I mean, in this matrix multiplication or aggregation process, my representation basically is related not only to my direct neighbors, but also to the neighbors that are located in the second row of the table. And why this happens? If you remind it, I mean, I said before that this process happens simultaneously, right? So basically when the knowledge coming from these orange nodes is aggregated here, at the same time, this orange knowledge received information basically from their connections. So in the first interaction, after the first interaction, also your knowledge is updated, guys, with the knowledge of your friends. So once we stack a new layer, the new knowledge that comes from you, it's not only related to you, but it's the resulting knowledge that comes from you and from your friends. So this is why when I stack a new layer, basically the resulting knowledge is this gradient colored node, which actually, the key idea is that I incorporate in some way the relational structure, the local relational structure of the graph during this, thanks to this, I mean, message update and message aggregated update process. So that's the key idea. And the final layer, this is actually a traditional operation, which is applied also to other types of architecture. But at the end of the day, we would like to be interested in obtain a final vector that actually represents the entire graph. So we use this readout layer, which is basically another permutation invariant function. So at the end of the day, the resulting graph, the resulting vector that represent our graph will not directly depend on how the nodes, where the nodes are located, right? So if we switch with you and you start you come here and I go to your seat, I mean, the final graph that is the result of our connections will be the same. So this is the key idea of the message passing neural network. Yeah, please.
So is there a possibility that we'll have cycles and we need to basically figure that out in this graph?
Yeah, that's a really good question, right? Because one of the, you have another present for you. You ready? Great catch. Yeah, that's an important point, right? Because one of the key limitations, right, of graph neural networks and one of the key limitations of aggregating at the local level of the features is related, I mean, generates a problem that is called oversmoothing, right? In the sense that if you imagine the process of aggregation, of aggregating with multiple layers, all the features of the nodes and all these nodes exchange messages. At a certain point, after many iterations, we will obtain some sort of the same representation for all the nodes, right? So this is why recently have been developed some algorithms and some architectures that are called graph transformer networks, which basically try to overcome this issue, basically not considering only the local dimension of the messages, but basically applying an attention mechanism that includes all the nodes in the graph. I mean, these in some way address the problem of oversmoothing, but as you can easily understand, when we have an attention layer that is longer as the number of nodes in the graph, there could be a problem in terms of scalability. So it's just a matter of trade-off, right? It's a matter between basically expressivity that we are able to obtain and scalability of the operation that we have to perform. I don't know if I answer your question.
So what's graph vector? Is it how you define it? Is it like a triple or what?
No, it's a collection of numbers, as we have seen at the beginning. So in this case, it's a vector of 4 elements in which we initialize these elements to a number that means something in terms of graph representation, at least in theory. So let's move to the code and let's understand how all this stuff is implemented in the PyTorch geometric library. Actually, this is quite, I think that we build the intuition to understand how a message passing neural network is implementing graph neural networks, in the sense that when you implement your GNN, you basically have to implement these three different functions, right? These 3 different methods. And you can see here, for instance, for the case of the message, as we have seen before, we basically concatenate the features of the target node, the features of the source node, the edge attributes, and so on. And this self.mlp stuff, it means we parameterize with a multi-layer perceptron this assembled message. Then we have the aggregation, and then we have the update function that you can see here, that in this case, the aggregation comes from the concatenation between my knowledge, my vector, and the vector resulting from the aggregation process. If you want to know about the scatter operation, well, this is quite intuitive in the sense that in order to understand what the scatter run in the aggregation does, let's consider that this is my vector input, right? My input vector. You see here that you have some numbers, and then you have an index vector, which basically says in which way these elements should be aggregated, right? So for instance, if you have a 0 here, here, and here, so in the first, second, and the fourth position, it means that the numbers in the inputs that are located in the 0 in the first and the fourth position should be aggregated and put in the resulting vector. So this scatter operation does something that is basically related to the aggregation process that we have described. So let's move to the layers. And I have to show a bit of math, but before, again, code. And the key idea is that this basically base code that you can see here, it is something that is implemented in order to basically create, for instance, a graph convolutional layer, right? In the sense that if you go to the PyTorch library and you would like to explore the implementation of these layers, In the original implementation, you will find something like this, right? In which you describe the message, the aggregation, and the update. Obviously, the library provides already built layers that comes from research literature. So you do not have to implement this stuff by yourself, but you have this GCN COM, which actually does it for you, right? So basically, it describes the operation of the message passing layer. And so in order to get to understand the differences, right, between a traditional multi-layer perceptron, so basically a traditional feed-forward neural network and a graph convolutional network, I mean, actually, it's quite easy to implement something that uses this one or this one. The only difference is that at the propagation level, in the sense that if you see here the forward propagation of a multi-layer perceptron, basically it takes into consideration only X, where X is the features of the nodes, for instance, within the graph. So if you remember the matrix at the beginning, this was the matrix of 0 and 1. And then it basically apply also the usual operation, linear layers, so a matrix multiplication, dropout, and other stuff. In the case of the forward propagation of a graph convolutional network and any other graph neural network, you see the difference, right? Because the input, it's not only X, it's not only related to the features of the nodes, but there is an index, which is something similar to what I've shown you here, that describe how the nodes are connected. So in the forward propagation, the convolutional layer will take both, right? We will take the node features and the relational structure in order to perform the message update and message aggregation and update. Yeah.
It's been forever since I've done this type of math, but could you check my understanding on this? The main reason why we're passing in the edge index is for efficiency of the calculation. You could just brute force it otherwise.
Yeah, I mean, in the sense that we can represent the relational structure in different ways, right? We can have an edge index, we can have an agency matrix, and the edge index, as you mentioned, is usually used for efficiency, right? Because usually an adjacency matrix that describes the relationship, we will see in a while, it's very sparse. But this is one of the reasons. The other reason is that we need an edge index because otherwise we cannot perform the message passing, right? In the sense that, as you have seen in the previous images, the edge index describes how we are connected. So describes how we can pass features to each other in order to obtain a final result in which the node representation in some way incorporates the relational structure of the graph. So this is the key reason of using the edge index.
Awesome, thank you.
You're welcome. So a bit of math, but then we will have a look at the code of a NumPy implementation of the layers that I mentioned before, graph convolutional networks, graph sage, and graph attention networks. But just to have just to grab I would like to convey the idea that this is our original equation, right? The equation that we have seen at the bottom of the slides before. And any of these architectures is actually a specialization of each of these basically original equation. For the sake of simplicity, right, we consider not a general layer within the network, but the layer 0, right? So the layer in which the features of the nodes and the edges and all the other objects in the graph are the initial ones, right? So our initial knowledge. So XY, it's my initial knowledge. XJ is your initial knowledge, guys. What a graph convolutional network does? Well, we can specialize these message passing layer equation in different ways, right? The first key difference is applying a sort of normalization element to the message passing, and I will try to build intuition about itself. And this normalization element actually consider the relational structure of the graph. Basically avoids that two connected graphs contribute too much to the representation of the other nodes, right? And I will try to clarify in a while. So this is the high level meaning of this stuff, right? And the other operation is just a specialization of the permutation invariance function, which is represented by this circle, which is a sum, right? So the key difference is in graph convolutional network as a specialization of the message passing layer is the usage of this normalization score and the usage of a explicit sum operation, which is permutation invariance, as we have understood from the previous slides. So this is the way in which this normalization is calculated. We will see in a while the code, but D basically it's the degree matrix. So the number, it describes the number of connections for each node, and A is the adjacency matrix. So basically it describes how we are connected. Why we apply the normalization process? Well, the key idea is that let's imagine our original structure here, right? In which, okay, it's too far, okay. But we are the graph, right? And let's imagine that I have to transfer my knowledge to yourself, guys, and you have to do the same exercise. The problem is that I'm connected to all of you, right? But you are connected to only me. So it means that the impact that I can have on the final representation of your knowledge is higher than the impact that your knowledge, because I'm connected to all of you. So the key idea of normalizing the contribution of my knowledge is that I would like to reduce my contribution because it means that it risks to bias all the representation of your knowledge, right? And if you think about in terms of discriminative and distributional stuff, the fact that you are connected to all of me, it doesn't say a lot of information about you, right? Because you are connected to all of me. So all of you have my knowledge. So it doesn't say too much about your knowledge. So this is why in graph convolutional network, they introduced this normalization score in order to balance, right, this behavior. And as you can easily understand and guess, probably, this behavior basically is fixed because it directly comes from the relational structure, and it will be keep fixed during the entire training process. So this is not a learnable parameter. This number will be the same during the training process. And this is a key difference compared to the graph attention network. So I would like just to show you this collab notebook, right? But just to see that I usually numpy and use the equation that we have seen in order to basically try to understand what happens at any step, right, within a graph convolutional networks. So the key idea is that we are, right, this relational structure. This is the adjacency matrix that basically describes the connections. So the fact that you have a list of one in the first row and a list of one in the first column, it means that all of you guys are connected to me. And also I'm connected to myself, right? So basically the final representation during the graph convolutional network is that I have to consider your knowledge, right? But I have also to bias my knowledge with my knowledge itself. So this is why you see the self-connections. And here you see how the basically normalization is computed, right? Using this equation. And this is, it looks complex, but actually it's not so complex in the sense that in order to be d hat, we consider this vector, right? In which each of these numbers represent the number of relationships that are in the graph. So 5, it means that all of you 4 guys are connected to me and I am connected to myself, right? So why this is 5? 1, 2, 3, 4, 5. You are connected to myself and to you. So this is why this number, your number are 2, because it's 1 and 2, right? And we put all this vector in a diagonal matrix, right? Then we take these numbers and we apply the square root. So you see the update here. And then we put the square root under the 1, right? So we get the number 1 on this number. And you obtain something like this. But I would like to focus your attention on this matrix, right? Which actually in some way is initialized in the same position of our original adjacency matrix, because you have here, right, initialized in the first row, first column, and the diagonal, and the same behavior. You can see the same behavior is here. But how these have an impact, right, in terms of scale the messages? As you can see here, the number that I now represent myself, it's not like 1 like before, it's 0.2, right? It means that in some way the contribution that I will provide to you guys will be low. And this lowness actually is related to the equation that I showed you before. So in some way we rescale, and this matrix, I think that it's quite clear, hopefully, to express this information, that the fact that the contribution that I will provide during the message passing layers will be less than the others, right? It means that my information will not be useful to create your knowledge about graph database. Because I'm not probably the smartest guy, right? Maybe I'm the funniest, so I have connection to all of you, but I'm not the smartest, right? So if my knowledge is biased, this operation without normalization risks to bias yours. So that's the idea of graph convolutional networks.
Can I ask a question?
Yeah.
Maybe it's a naive question. I'm curious if there are multiple edges between a single node, how does that play out? Or basically, what kind of assumptions do you have on the edges that connect the different nodes?
So your question is if we have multiple connections between the same
you have two nodes and you have multiple connections.
Yeah, this is an interesting scenario, and I will give you the sock. I don't want to kill anyone, so I come closer. Yeah, this is an interesting point, right? Because if you think about how the message passing layer works, we consider just one edge, right, between two nodes. And the idea is that the connection with this edge actually is represented by a single edge index or a single adjacency matrices, right? So when you want to model multiple relationships between the two nodes, one of the key possibilities is using different adjacency matrix, each for each type of relationship, right? So at the end of the day, you will not have just a matrix representing relationships, but you will have a tensor, right? In which each, the first dimension of the tensor represents the relationship with this type, right? So this is a possible way. Obviously, this has an impact in terms of scalability, because now you do just not have a single adjacency matrix, but you have a tensor, and you can have multiple, right, adjacency matrices, and the number of the adjacency matrices is related to the number of relation types, right, that you have within the graph. So this is something that could be done, right? Python Geometric actually provide a heterogeneous version of all the layers that I show you right now. So I mean, this is operation could be done that should be considered, but we have to consider the scalability aspects.
Can I ask a question?
Yeah.
So in the example that you show, you're like, this is the center node, and then you're like, I have a layer here, and then I have another layer, and then that's going to kind of propagate that information down. So in practice, how do you choose like which nodes are like those center layers? Like, you know, the center nodes where you have the information propagating down to them?
Yeah, actually, I mean, I choose the central layer for the sake of simplicity, but there is the notion of sorry, not layer, but node. There is no notion of central node in the graph. In the sense, the operation that you have seen is actually performed for any nodes in the graph. So basically, any node is a central node in some way, because we use its knowledge is transferred to its neighbors, and this operation is due in the opposite direction. So the idea is that every node in the graph is a central node because you receive the messages from all its neighbors.
Thinking like that PyTorch, you can filter out classes and elements of classes. PyTorch geometric. Once you get into the header object.
Yeah, exactly. You can decide which nodes have to pass messages, right? Yeah, please.
Yeah, so you were talking about bias and such, but my thought is not all the nodes might have the same level of accuracy or good knowledge. You know, it's how do you account for the those nodes that, you know, for instance, if I was one of the people in your matrix and we were talking about like these equations, I don't know math, but I transfer my knowledge to you, it's not going to be as valuable. Is there a way to account for less value in a node or in the knowledge that's being transferred that
Yeah.
we should be biased where we don't want over bias, but on the flip side, you know way more about math than I do, so. what do you
Yeah.
want?
Yeah, that's a good point, but that's the problem. The problem and the opportunity with representation learning, in the sense that, as I said before, these messages basically are parameterized. So basically they will be learnable. And the key idea is that in theory, the learning process should update this representation in order to perform the downstream task. So the key idea is that we cannot know a priori if this node includes good knowledge or its features are in some way biased or contain some errors. We cannot know, but we can try. The exercise that we can try to do is, okay, let's try to learn, starting from these initial features, to learn an updated representation in order to solve the downstream task. But obviously, this will not solve the problem at the origin, right? As you mentioned. But this is the exercise that is done during the training process.
Could you pass like their confidence?
Yeah, in the sense that in the feature vector, basically you can incorporate any information that you want, right? In the sense that anything that you are able to translate in a numerical representation can be used for the features. I mean, in theory, the representation learning process should help you, right, in gain and obtain the representation of the nodes that could be effective. But I mean, in research papers and in activities in real scenarios, people notice that effectively incorporate some initial features, some initial valuable features into the nodes could help, right, the training process, also considering the message passing layer. So, but in any case, any information that can be translated in a number, and now everything can be translated in a number because we have this embedding stuff coming from a large language model, could be incorporated as a node feature. So let's, yeah, please.
Before you said like in your example, the 4 nodes were passing knowledge to the main one, and also the previous one. Is there a specific number of steps, like just maybe the 2 previous nodes that are passing knowledge to the main one, or like you are getting all the connection?
Well, in the
different possibilities.
yeah. Well, in the message passing layer, basically the number of hopes is an hyperparameter, right? So you define a priori the distance of the nodes from which you want to receive the data. Some of these techniques, including graph sage, actually apply some sort of sample of the neighbors. So basically, you define the number of hopes, but at the same time, for each layer, you define the number of nodes that actually provide you information, right? So probably in order to speed up the training, not the information from all your neighbors should be used. Obviously, they are selected as using a probability approach, right, in terms of sampling, but this could be useful when, I mean, to improve the training efficiency. I have a talk for both of you guys. We have just 2, right? So feel free to ask. I try.
Can you comment why is it convolutional? We have some pattern kernel going in the matrix and multiplying to get the result. So how is this convolutional?
Because it's a terminology that is taken from the convolutional neural networks, in the sense that basically when you apply a convolution at the local layer, at the local level of an image, in some way the information of the pixel are translated, right, between the local dimension. Yeah. So this locality this key idea of locality is in some way translated to the graph neural networks because you get information from your neighbors, which in some way are the pixels that are close to you in the images.
So graph represent locality, then ages represent the fact that in the world of their space of whatever it is, instead of matrix. But like, can you do the same with just having a matrix, just having weights increased in certain places? Is it?
Yeah, but you need the information about, because in the case of images, you have a grid structure, right? So you can easily detect your close pixel by just moving, right? Increasing some, basically the coordinates, right, of the stuff, so in the matrix. But when you have a matrix, I mean, you need a representation of the relationships because you do not have a standard and well-defined geometrical structure, right? So this is why graph neural networks incorporate the edge index dimension, because you do not have this notion of locality just looking at the data itself, because let's imagine that you have a plane representation of the nodes in a matrix. You cannot see how these nodes are connected to each other, right? So you cannot know a priori how to perform the convolution, so you need another ingredient, which is the edge index or the adjacency matrix or so on. So that's why it's called convolution, and that's why this notion of locality is expressed using the relationships. Okay, let's move on. So, I mean, the only thing that we have to know about graph sage is that the permutation invariance function is an average, is a mean about the node features. As you can easily probably guess, basically the final representation of the local structure does not change if we make the sum or if we make the mean. An interesting thing is actually related to how we parameterize stuff, because in the traditional message passing layer, you have just this psi, right? Yeah. But in the case of the graph sage, the original implementation used two different weight or parameter matrices, C1, C1 and C2, right? And why it is done? Well, because graph sage actually has been developed in mind, with having in mind the recommendation systems, right? In which, if you think about Netflix, right? I'm not connected directly with all the other users on Netflix, like in Facebook or Instagram or whatever. The connections that I have is that with the movies that are in the platform, right? So the reason of using two different parametric matrices is that I want a representation for the people, right? But then I want a representation also for the movies. And we cannot use the same vector space because in the real world we represent different objects. So the distributional representation of myself should not be connected in some way to the movie, because a movie is a movie and me, I'm a person. So the fact that we have the similar representation potentially doesn't mean anything, right? Because I'm not similar with a movie, I mean, in terms of representation of the entity or of the object. So this is why they decided to use two different stuff. But here we have the concatenation. I will not go through the code because, I mean, for me, it's just important that you grab these differences, right, in which we have different parameter matrices considering this reason. And that's the main difference between graph sage and a graph convolutional network. You have a Colab notebook, which is similar to the previous one, in which you have the NumPy implementation step by step of the graph sage layer. Okay, graph attention network. So I hope that you get a better idea about how all this stuff work, about how are different graph convolutional network and graph sage. For instance, in graph sage, you do not have this normalization performed with that operation, right? Sometimes the normalization operation in graph sage is simpler. It just considers the degree to normalize the contribution, right, of each vector. But let's talk about the graph attention network. I mean, the equation becomes really complex, right? But the only thing that I would like to convey in terms of understanding graph attention networks. As you remember, when I talk about graph convolutional network, basically this normalization process, I said that it's stable, right, during the training. So it means that the numbers that describe how much I contribute to the knowledge of my neighbors and the opposite stuff remains the same during the training process. What graph attention networks tries to do is also updating, right, the contribution. So during the training, the weight of my contribution to my colleagues change over the time in order to satisfy the downstream task requirements. So based on this behavior, you can guess and you can imagine that the number of parameters is different. Right? We just do not have the parameters to parameterize the messages or the aggregation operation, but you have a parameter in order to rebalance, right, the weight of my contribution, which in graph convolutional network was stable. So as you remember, I'm not the smartest guy in the room, so my contribution should be reduced because I connected to all of you and my knowledge risks to bias yours. This contribution actually is in graph attention networks balanced, right, in order to satisfy, as I said before, the downstream task. So it means that, I don't know, for node classification, if my contribution during the training becomes really important to obtain the results that I expect, so the level of my contribution will be higher and higher during the training. So this is the key difference between graph convolutional networks and graph attention. The weight of the contribution changes over the time in order to satisfy the learning process, right? The expected result from the learning process. Also for this, you should have the collab somewhere here. Okay, so you have the collab notebook and you can check how this operation works. Right? Yeah, please.
When you were talking about debiasing your knowledge in the beginning, is that within the math that sets the value by which you debias, and then when you're saying you rebalance, is that all in the math where it debiases and rebalances, or do you set some sort of initial value yourself as to how much you want to be debiased?
Well, in the graph convolutional networks, is biased at the beginning, and it depends on the relational structure. So I don't have an initial starting number, but the way in which my contribution to the knowledge is biased depends on the relations. And as I mentioned, basically, if I am connected to many nodes in the graph, my contribution should be reduced because I risk to bias the learning, right? While in the graph attention network is the same. So at the beginning, actually it's a bit different. It's in the sense that you initialized in a random way how my contribution should be biased. But then these initial numbers are adjusted, right? I mean, to satisfy what I mentioned before. So that's the key idea. So applications. As we mentioned, right, there are some standard and traditional applications for graph neural networks, including node classification and link prediction. And this is a typical workflow that we can basically specify in order to address node classification and link prediction problem. Because if you think about a simplified version of a node classification, which means I want to assign to a node a 0 or a 1 label, so binary classification, because probably I'm basically analyzing a payment network. So I want to understand if this guy is licit or its behavior is licit or the other behavior is not licit. So this idea of 0 or 1 can be potentially applicable to link prediction, right? I would like to predict if a link exists or not exists. So when you have this type of problem, actually you can treat your approach, you can use a similar approach, right? Because there is a similar problem. And this approach actually includes multiple steps. The first one is basically an understanding of the input data. I mean, the input data that you require for graph neural networks is usually quite simple in the sense that you usually have a CSV file with 3 columns, in which in the first column you have all the subject, right, of the triple in terms of ID. In the no, maybe two columns, right? You have the source in the first column and the target in the second column. So it's quite easy to represent connections in a CSV file, right? And this file actually represents my edge index. And some of you may ask, okay, but if I have graph databases, how all this stuff is connected to graph neural networks? Well, it depends in the sense that when you run machine learning algorithms, basically everything runs in memory, right? So graph databases are useful when you need a persistent layer of your data and when you want to perform queries. But when you run graph neural networks, this is not, I mean, key component, right? Because in theory, I have to transfer all the information from the graph databases to a representation that can be understandable by the model. So some graph databases implement some graph neural network algorithms. This is possible, but it's not necessary, right? Because at the end of the day, I want to have a raw representation of my data because this data should be transformed into matrices in order to perform the learning process. So you usually have a simple version of the data when you have to work with graph neural networks. And then you have the graph processor component, which is something that is basically implemented in Python geometric, in the sense that from this raw data, you want to create a new object, which could be an homogeneous graph or eventually an heterogeneous graph. So to answer to your previous question, basically, you can represent a graph having multiple types of relationships using this Python geometric heterogeneous object. And the third main step is the encoder, right? The encoder means I want to apply basically the message passing layer. So I want to perform the operation of the graph neural network in order to obtain a representation before the real training, which in some way incorporates the local neighborhood structure, right? So the key idea of the encoder is, okay, I perform the message passing layer. I perform what we have seen until now. And then we have a decoder, right? So what I will like to do, right, with this new rich representation of my nodes, and this is the layer, this is the component in which I perform the real task, right? In the sense that until here, basically, I decided to aggregate, right, the information based on the encoder that I prefer, graph attention network, graph convolutional network, beyond the prediction task that I want to perform. But at this level here is where the training process starts. So I obtain this rich representation. Now I want to do node classification or link prediction. So the training starts, and these rich representations start to be updated in order to satisfy, for instance, the supervision process that I have at the node classification level or the link prediction level. So this is a common architecture, an encoder-decoder architecture that could be applicable also to other, I don't know, transformers or other stuff, but that in some way identify the main phases, right, of using graph neural networks on my data. That's the idea. And finally, obviously, we should be able to obtain a trained model, which could be used, right, to perform the inference step. So in theory, this model should be able to classify nodes or to predict links in the right way compared to the model before the training process. So node classification. What happens in node classification? As I mentioned before, this is a common framework, and then we have to specialize this framework in order to address the node classification. So these are the main blocks that are important for this step. We create an homogeneous data in our context because we will work with Bitcoin data in which the nodes represent the transactions while the edges represents the payment flows. So we will build an homogeneous data. We will use an homogeneous graph neural network. So a graph neural network that uses only a unique adjacency matrix or a unique edge index for the aggregation process. And then we will use this combination of log softmax and cross entropy loss. The only thing that you have to understand about log softmax is that at the end of the neural network, once I obtain the representation, the log softmax basically apply a score, a final score to this representation. I mean, its value, its range is between 0 and 1. So the feature vector is transformed into a number in between 0 and 1, and then the training process try to enforce in order to classify the node as 0 when the node is licit, and the node as 1 when the node is illicit, right? This is something that is traditional use for any type of classifications.
It's all the same. Do they have the same activations? They're all similar.
Yeah. This is just the readout part, right? So it's the final part.
For the nodes itself, this is the end of the whole graph.
Yeah.
That's forward, or this is the quadrant.
Yeah.
Nodes itself, they're all the same. They have the same activations. So the
we just use the algorithm as it is for all the nodes, so we have the same. So this is the idea, right? And this is the process that we'll use for preparing our data. So from the source data, in which you have 3 distinct files, right? You have a file related to the features of the node, which in case of Bitcoin, it's a vector of 160 elements that are anonymized, right? So frankly, I don't know what they mean. But then you have an edge list, right? And then you have the classes, because you have to know, because this is a supervised classification problem. So basically, we have some nodes annotated as is licit, as illicit, as unknown, right? So this is the third data set. And then you have to perform some transformation in order to obtain numerical and matrix representation of the data. Because as you remember at the beginning of this masterclass, basically, we just have seen matrices, right? When we had to understand all the aspects related to the parameterized stuff. We talked about edge index, we talked about adjacency matrices. So everything needs to be translated into matrices. And then when everything is translated into matrices, then we can use the homogeneous object in Python geometric in order to incorporate these matrices into Python geometric. And then an approach, right, to create the traditional 3 distinct data sets is applying a node masking, in the sense that in the homogeneous graph, you basically have all the nodes, right? But then you need some masking operation to decide which node should be used for the training, which node should be used for the evaluation, and so on. So this part, right, is traditional ones, in the sense that if you look at the PyTorch code, the traditional code in which you see all the operation, optimization step, and so on, this operation is the same for any training process, right? But in the case of graph neural networks, what changes is this idea of aggregating features from neighbors. So this part is the same for any type of deep learning training process that you could see, right, and that you can find. Okay, let's have a look at the code, right, in which I basically show all these operations, so you can have a more concrete intuition about them. I mean, the code is quite complex, right, in the sense that it requires a lot of operations. It's not like working with LLMs, right? I'm sorry for that. But yeah, I would like to just to focus on the main parts of this code. Let me zoom in. Okay. Okay, here you have the import stuff. Then you have a part in which you download the data set. The data set that we use is called elliptic, which is basically a photograph, right, of a Bitcoin network in a certain instant of time, right? So you make some pre-process stuff, right? And at the end of this, at the initial, in the initial phase of the data, you have the 3 different CSV files that are structured like this, right? For the features, as I mentioned before, we have 200,000 rows, which represent the nodes with this number of features. Then you have the classes, right? And then you have the edge list, right? In which the first column represents the source node, and the second column represents the target node. And then we apply some operation in order to understand how the labels are distributed within the graph. So basically, for the 77% of the nodes, we do not know the label, unfortunately. We know that the 20% of the nodes is licit and the 2% is illicit, right? So this is a typical structure that you have when you work with machine learning algorithms. And then you apply other operations. As I mentioned before, this is interesting because as you can see from the first row, the indexes that describe the original data are remapped to numbers from 0 to the numbers of nodes. Because you have to consider, okay, I have my data, but I have to represent them in matrices. And if you remember, I have to represent, for instance, the node 0 in the first row. So I have to indicate this node here as 0 in order to locate the data in the right way for performing operations within the matrices. Okay, this is not so important, but this is the way, right, in which we create an homogeneous object within Python geometric. It's quite simple, right, in the sense that once you have pre-processed your data in terms of features, in terms of edge index, and I reminder that making the edge index, it means remap the indexes of your data in order to they can be ready for a matrix representation. And then you have the labels, right, assigned to the nodes. Now this object is ready for the training. So what I wanted to do right now is that, as I mentioned before, I applied the mask. So I have to decide which nodes are used for the training, which for the validation, and which for the testing. Yeah, this is still data preparation, and then we perform the training, right? So we can select the models that we want to use. Obviously, in this notebook, there is not the entire code, but there are some libraries that I wrote in order to use this way in order to run the algorithms and run the models. But then you have some of the models that we have discussed before, right? Graph convolutional network, graph attention network, and graph sage. So we run the training in the traditional way in which we train any deep learning model using PyTorch. We obtain some results, but I would like to focus on this, right? The number of parameters, which has a direct impact on the efficiency, on the duration of the training, right? In the sense that here, you have the number of parameters of graph convolutional networks, so 2000 and so on. Here you have the number of parameters of graph attention networks, right? Which is one order of difference compared to the graph convolutional networks. And this is related to the fact that, as you remember, basically the weight that we assign to the edges is also learnable, right? So this has a huge impact in terms of number of parameters that graph attention networks have. For the graph sage, we have, just a bit higher number compared to graph convolutional networks. And if you remember, I told you that in graph sage, we use two different weight parameters, right? One matrix parameter to represent people and one matrix parameter to represent movies, for instance. This is why the numbers is a bit higher than graph convolutional networks. So we perform the evaluation, but I would like just to show you the last conclusion matrix to understand, because we would like to understand which model performs better, right, on our data. So this is one dimension that could be taken into consideration. It's not the only one, but what we would like to basically obtain is usually, we would like to obtain a high accuracy in detecting illicit nodes, right? Because we would like to get and identify which are the nodes that represent anomalies in the graph. So the numbers that we have to take into consideration is that one, right? So the cases in which the predicted class of my model is illicit and the actual class within the data is illicit, right? So there is basically an overlap between the result of the model and what the data says. So considering this implementation, you can see that this is graph convolutional networks. This is graph attention networks. This is graph Sage. This is GNN, but it's not so important. This is just another architecture. So we notice that graph Sage actually obtained 84% of accuracy on the illicit nodes, right? As you can see, all the result for the licit nodes is very high because obviously considering the distribution of the data, it's easier to predict that this node is licit because it represents the 80% of the data, right? But graph Sage can be taken into consideration, right, in order to select which model we would like to use for this specific task. So that's the idea. You have the notebook, you can play with it, right? And you can decide, you can also play with the hyperparameters, I think. I mean, augment the number of epochs of the training, change the dimension of the layers in the graph neural network. So feel free to play with it, and the notebook is available on the GitHub repository, the link. Regarding the link prediction, I am almost done actually. I mean, this is another way to see what I have explained so far. Regarding the link prediction, again, we have the same framework, right? But we have to specialize in different way. Consider, compared to the node classification task, in this case, for our choice as engineer, we can decide to apply an embedding model before the graph neural network model. What does it mean in terms of architecture? It means that we have our initial features, right, of nodes, and then we want to apply a new layer that transform these initial features before performing the graph neural network propagation, right? So this is something that you can apply in order to augment, right, the expressivity of your data if you do not have a rich set of initial features. And this is what is done in this case in the context of link prediction. It could be done also in the previous step, right? But as you remember, we have a quite long vectors, right, that represent the nodes, 160 features. But in this case, this vector is not long, right, in the same way. So we can apply this embedding model. And then we apply a decoder step in which we have a dot product. And this link prediction is performed for movie recommendation, right? So basically the dot product means you have a vector of the users, you have the vector of the movies, you multiply these vectors element by element, you sum the results, and then you adjust these results during the training in order to see, in order to understand if the link exists or not, right? So this is the process, a bit more complex compared to the node classification. But the interesting thing is at this level, right? Because it represents a key difference compared to the traditional machine learning approaches, in the sense that you have the 80% of the data in your training set, right? But let's think about how graph neural networks work, right? Graph neural networks explicitly leverage the links in order to perform the node aggregation of the features, right? So these links are explicitly used for the message passing. But think about this. If I used to understand if this updated representation should be useful to say if a link exists or not, this is a bias, right? Because I already performed the message passing, so I already use the existing links to transfer the features, and then I ask, okay, is there a link? But I perform the message passing, so the link exists, right, by definition. So what is done in the training set is usually I select a portion of the training for the message passing, right? And the remaining part of the training set is just used to perform for the evaluation within the training, in the sense that the remaining part of the training nodes have not been involved in the message passing layer. So they could be an interesting example to understand if a link exists between them, right? because they do not be involved in the message passing layer. So I did not go into this bias in which I use the message passing layer with the link, and then I ask, okay, is there a link? But I did the message passing layer, so the link exists by definition. So this is a different way compared to traditional machine learning that basically involves the learning process in this scenario. For the node classification was a bit different because I don't want to predict links, I want to predict label on the nodes. But here I want to predict links that are used for the message passing. I don't know if it's clear enough. I mean, sort of.
How much do you reserve for evaluation in the training set at that point?
I mean, basically you can think about that the 70% of the 80% is used for the message passing, and the remaining 20% within this 80% or 30% of this 80% is used for the evaluation on the training, right? So 70-30 within this set, yeah.
The example that you gave with the Bitcoin data set that was so unbalanced between the classes. So do you have to do something in a case like that? So if then again you're resampling within the training set, then you risk like getting just a bunch of like illicit things, and or do you do something before that?
In this example, I didn't do anything before that, but you are right? You have to consider, I mean, in theory, if your graph is large enough, this should be a fair operation, right? But you can probably decide, right, how to split within the training set the information that are used for the messages passing and for the evaluation. This is something that it's possible. But usually when you have a large graph and you start to sample the neighbors that you want to use for the message passing and you make this operation, maybe you should rebalance in some way the graph distribution. You should. I mean, yeah.
What is the correct minimum dimension that we need in order to not overfitting or like have the problem that it was saying?
Yeah, that's a good question. I mean, as the previous one. Actually, I didn't see a lot of literature, right, on this, right? But yeah, I don't know if it's fair enough, but I usually follow the PyTorch geometric tutorial and see how they split the data, and I guess that this is the right way in which you have to do the stuff, right? But I mean, it depends from a lot of factors, including, I mean, the relational structure of the graph. But frankly, I do not have the right direction, right, to go. Yes.
Just repeat this process a couple of times and see how much your output measurements vary based on how you do this. Gives you a sense of where you're getting stable results.
Yeah, I mean, you can treat, as you mentioned, as an iterative process as any machine learning techniques, right? If you gain the experience to understand which are the hyperparameters to obtain such valuable results, otherwise you have to test. And I mean, there are a lot of tools, right, that track your testing. Yeah, that could be a way, definitely. Okay, so let's move to the code, right? I have 3 minutes. Yeah, the code is actually very, I mean, it's not similar to the previous one, but it makes the same operations, right, in terms of data preparation and so on. The only difference is that in that case, as you have seen before, I had an embedding layer to the information representation, in the sense that I have no initial features for the people, right? But I have initial features for the movies, right? Because you have the genres. So the key idea in this case, I translate these basically genres information as a vector, and I initialize with a 1 if, for instance, the movie involves this genre, right? So let's imagine that the adventure is the first element of my vector. It means that for movie 1, I initialize 1 in the first position. I do the same 1 for the second movie, so for the second position, but for the others I put 0 because they are not adventure movies, right? So this is a very traditional operations. I would like to go, you can have a look at the code for the training. I would like to go for on the final results, again on the confusion matrices. And you can see that probably if your final object is to predict if a user will like the movie, we should consider this quadrant, right? So basically the way in which, the case in which the model predicts correctly an existing link. And as you can see from the results, in this case, and it's quite interesting, in this case, graph convolutional networks performs better, but graph sage is quite close, right? Probably this number can change if you make different experiments, but the key idea is that graph sage and graph convolutional networks are the best operation to perform this stuff. And that it's interesting, right? Because empirically, this is against the tendency of saying, okay, if we have more parameters, like in graph attention networks, then we obtain better results, right? There are some cases like the one that we have seen in which it doesn't happen. And why it doesn't happen? Well, in this case, because we have a very sparse graphs, right? In the sense that we have many nodes, but you do not have a very dense connectivity between these nodes, right? If you think about the transactions, I mean, for a huge graph, you do not have nodes with a lot of connectivities. I mean, nodes that receive a lot of payments or perform a lot of payments, right? So this is probably why graph attention networks does not perform very well, because the connectivity is not so high. So learning the representation of the edges, learn the representation of and the weight of the contribution, it's not so important for these specific tasks. So this is something that you can have in your mind, right? For I mean, understanding which model could be better than the other. I would like to finalize my presentation. Unfortunately, we do not have too much time, but with this model, this approach, this is called GRetriever. So this GRetriever model actually has been basically developed by multiple researchers, including Jan LeCun, the chief AI scientist of Meta. So I thought that it could be valuable in some way. And the key idea, one of the key problems, and you will hear a lot about this problem during this conference, is about chatting with your graph, right? So basically the key idea is that you have a graph, you want to interact with your graph, you want to interact in a chatting way, right? So all this stuff that you heard about graph RAG and so on, it's to try to extract the valuable knowledge that is located in the graph in order to retrieve information in an easy way. And the traditional way in which the RAG works includes potentially this step, right? You have a user that it is interested in getting an answer about something. You have potentially, I mean, a basic RAG system or an agent. And this agent try to leverage different tools, right? And these tools could be the traditional vector database, like Weaviate or or other database like that. And so in that case, you perform your query in natural language, and then you receive response from the vector database. Then the other step is that, but my database actually is also a graph, right? So what I would like to do is to generate a query that could be a Cypher or Sparkle query in order to retrieve the information and combine the information potentially with the details coming from the vector database. And so I can obtain a response. But the missing pieces potentially could be another component, right, which is a GNN semantic retriever, in which the embeddings that are exploited are not the textual ones, or not just the textual ones, but also the embeddings that come from the message passing layer result. So this could be considered the missing piece, right, in GraphRag, at least for my own humble opinion. But as you can see, it will be difficult to incorporate in the sense that we have seen the complexity of graph neural networks. We have seen how the architecture depends on the data. So this is something that is hard to implement in terms of costs and potential revenues, I would say. So for now, the research is going, is try to explore this idea. And this is the main architecture of this GRetriever stuff. The only thing that is important compared to traditional approaches is that let's think about the training or the fine-tuning of a large language model, right? In a fine-tuning data set process, you usually have your question, right? And then you have the expected results. The key idea is that if I have a question on the graph data, the other thing that you would like to incorporate is a graph soft prompt. We usually use prompt talking about, textual instructions, right? But this is usually considered hard prompt. But when we incorporate soft prompt, it means that we concatenate to the textual information also the embedding representation, in this case coming from the graph. So the key idea is that I have my question, I have my answer, but with the question, I incorporate some learnable embeddings that can be updating during the training. So the key idea is that this much more information could be useful, to improve, right, the final results that I obtain from the fine-tuning process. So basically a system that is more accurate because it combines also the graph representation of the data. So we do not only apply embedding techniques to the textual information, right? So for instance, to the name of the nodes or to its description, but we also try to incorporate, right, a vector that do not come directly from the textual information, but it directly comes from a graph neural network. That's the idea. That's the idea of the model. And yeah, I do not have too much time, right? So I'm going to the end, and I will left basically a Colab notebook that you can explore. Actually, it's used actually a paid version of Colab, so I don't know if you could run it with a standard. But in any case, right, basically the guys from Python Geometric started to incorporate this model in their library. So for instance, here you have the graph attention network, you have the LLM, which is Llama 2 in this case, and then you should have the call here in which you call GRetriever inference in order to basically use the embeddings coming from a graph attention network for the process that I have just described. If you would like to have more details, I will be around here until Thursday, as I mentioned before. And before you leave, I would like just to share with you that I'm writing a book called Knowledge Graphs and LLMs with some of my previous colleagues. And using this code, KGConf25, you will have a 45% of discount of this book and all the other books from Manning. You can use this link if you are interested in the book. And we talk about a lot of stuff, including graph RAG, including building graphs in an automatic way, extracting structured information from unstructured content. We talk about RPG, RDF, and so on. Or if you are interested in these topics, you can buy the book. And I would like to thank you very much for your attention. I hope that you will be able to get a better idea of graph neural networks, which should be something less obscure than before. And yeah, thank you very much.
I do, I really like it. I wish we had a little bit more.
Okay.
J1.
But you mean RAG in terms of graph RAG or traditional? Graph RAG.
Unmuted testing.
Yeah, yeah. Yeah, I mean, I know the lang graph basically implements a lot of
No, I just like need a
basically methods to generate a query, right, to interact with your graph. So basically, the natural language question is translated into a cipher or spectral query, and then the results. Yes, I see that Neo4j, but also other vendors are investing a lot in their own library for the graph RAG, but I mean, the accuracy is still low in the sense that, especially I noticed in the direction, in the sense that you pass the schemas to the model, so the model is able to identify which nodes and edges should be. Yeah. Yeah.
All these things are like, I
Yeah.
want it to be really messy, I want it
Yeah, I mean,
changing at all times, I want it to be private, and like.
yeah, no, I mean, it's still an open research direction.
Makes sense, it's like drug discovery.
Yeah, I didn't test it yet, right? But I think it should be one of the mature projects.
Maybe like,
So, yeah, I think that I would
like,
give it
right
a
now,
chance
right, like,
for
this is great.
experience.
But yeah.
Thank you, bye.
Great talk. Like,
Thank
one
you.
of the big things.
Very, very helpful.
Great.
And to give you some ideas from our team,
Okay.
9 years ago, the general tenor of your work is very well interfaced with things that we're building. So I would love
Okay.
to later catch up with you and see if we can potentially bring you in to talk about that role and that.
Yeah, it would be great, and thank you very much. So, yeah, I will be.
I'll track you. I'll track you.
Yeah. Thank you. Thank you for being here. Thank you. Yeah. Yeah, we can take some time to go there and we can see the slides together if you're interested in it. We can have a look also at the code.
It's like all of our.
Yeah, because there was not much time, right? So I have to close and.
I know.
But one ask a question about retention. Their training for the nodes are happening at the same time as waits for the connections in the computer.
Yeah.
Why would it end at the same, why would it train with the same speed?
But you mean in traditional GNNs or in?
Graph, that's right, we had an encoder that learns their connections.
Yeah, I mean.
It's not, like, because they're not really independent. If nodes are learning while.
Can I ask you to, because I'm
Yeah.
trying to set up the next one.
Yeah, yeah,
Thank
yeah.
you so much. Continue the conversation, but I just want to.
Yeah.
And then tell me your microphone.
Yeah.
I'll take care of you then. Yes. So thank you. Appreciate it.
Yeah, you're welcome.
Your ideas already did. Yeah.
Can I just pack my stuff and then we can. Thank you, appreciate it.